Okay, so hello everyone again. This is the second lecture on motion in a plane. In the previous lecture, we have started with the graphical explanation or graphical method of addition and subtraction of vectors. So we will continue with that discussion. So let's move forward. So I'm Samir Lawankar. Let's begin our discussion regarding the second lecture on the series, that is motion in a plane. Okay, so just a course outline for you first of all. So in the course outline, right now we are on the topic, we are on the fourth topic, that is addition and subtraction of vectors by graphical method. We understood that is in introduction part, we understood as in how it is different from motion in a straight line. We just increased the aspect, brought to basically two axes. This can be also increased to three axes, basically in 3D space. We won't go into that complexity right now. We will understand only for 2D space here, and then we can move further. Okay. And in second thing, we understood the basic difference between scalars and vectors. Each and every point was made you understand in great details, as in what is scalar, what are the examples of scalar, how is the algebraic addition, subtraction, multiplication, etc. are being done for a scalar. And now we are basically trying to understand how it is being done for a vector. The basic definition of vectors are completed. We understood several things in this, such as this third point, that is multiplication of vectors by real numbers. And right now, let us start with the discussion about fourth topic, that is addition and subtraction of vectors by graphical method. Once this is done, we will understand a small topic which is called a resolution of vectors, so that we can understand the main mathematical analogy, that is analytical method of addition, vector addition. Okay, so let's start. Fine. So we have in the previous lecture we understood that this is how we can understand the triangle method of vector addition, and this is the vector A, this is the vector B, and the resultant is this, that is R is equal to A plus B. Okay, so that thing is also being explained here. Okay, so now let us begin with the further discussions now. Okay, so if we find the resultant of B plus A, then the same vector R is obtained. Okay, so they are just saying that, let us say, so basically what we had was, let us say this was some vector A, okay, and this was some vector B, correct? So now what we did was, first of all, in this scenario, what we did was, we did vector A, so this was some vector A, and then we kept the tail of vector B on the head of vector A, and we got the resultant, that is nothing but R is equal to A plus B. This time we are doing a little bit different. This time what we are doing is, we are doing B, and we are keeping the tail of vector A on the head of vector B, so that this time we are getting a resultant which is like this. If you see clearly, R has the same magnitude, the resultant has the same magnitude as that of the previous R, and the direction of this is also same as this. Okay, so there is no difference between A plus B, so A vector plus B vector, or B vector plus A vector. So there is no difference between A plus B and B plus C. Hence, from this we can understand that vector addition is a commutative. So it has a commutative property. What is commutative property? Basically, the property says that A plus B is nothing but equal to B plus A. Fine. So that was an explanation of one property. Just to understand again, so just to make you understand again, so whatever we are doing basically is that this is some vector A and this is some vector B, let us suppose, and we need to do A plus B. So what will we do is, we will just add, we will keep vector B like this, and hence this will be our resultant vector. Okay, so that is how we try to do vector addition, and because a triangle is being formed here, hence we call it as triangle of vector addition. Okay, so the next line says that the addition of vectors, please refer to the third line here, the addition of vectors also obeys the associative law as illustrated in figure D. So now let us try to understand associative law. So in algebraic expressions also we know that A plus B is equal to A plus B plus C. Okay, so when we understand this same thing being able to understand with vector addition also. So basically, as you can see here on the figure D graph also, that the result of adding vectors A and B first. So let us first add vector A and B. How will we add vector A and B? Let me explain to you clearly. So let us suppose that this is your vector A and this is your vector B. Okay, so that means that this will be your resultant vector A plus B. Correct? Now what we are doing is, with this resultant vector we are adding vector C. So at the tip of this we just kept vector C, and therefore vector R plus vector C will give you vector A. So this may be a little difficult to explain. I will go and explain it again. So let us suppose this is the vector A and this is the vector B. Okay, therefore what will be the resultant? Resultant will be nothing but this, which is R is nothing but equal to A plus B. Fine. Now let us keep R is equal to A plus B here. So this is nothing but R is equal to A plus B, and let us keep C. Let us add C to this. So if we add C to this, then this will be the final resultant. Let me write this resultant as some another quantity called as P. So what will be this P? So basically what we did A plus B and then we added C to it. Okay. Similar way, if we try to add first B plus C and then A into this, so let us say what we are doing is, so A was like this, if I'm correct, B was like this, correct, and C was something like this, correct. So let us first add B and C. So if we add B and C, so this will be B yours and this will be your C. Okay, therefore this will be the vector. Let us suppose we are writing this as M. So M is nothing but your B plus C. Okay, so I'm just simply following the rule of vector addition, nothing else. Okay, now if I need to add A into it, what will I say? Let us make it here. So let's say this is your M, which is equal to B plus C, and I add vector A into it. Okay, so if this is that vector A, then this will be your resultant vector R, or not R here. So let me use some another symbol for it. So this will be, let's say M and P, let's say Q. So this Q is A plus B plus C. So if you view correctly, then this Q is equal to the resultant value of bracket A plus B in brackets plus C obtained previously. Okay, so that is how you can understand this all concept using the normal graphical method of addition of vectors. Okay. So the resultant of adding vectors A and B first and then adding a vector C is the same as the result of adding vector B and C and then adding vector A. So basically what we understood from this is that A plus B in brackets plus C is equal to A plus in brackets B plus C. Okay. Then is what is the result of adding two equal and opposite vectors? What does it mean? Equal and opposite vectors. Okay, so opposite as in the direction is only reversed. Okay, so let us understand this by the following example written here. So consider two vectors A and minus A. What does it mean? So we have some vector A, we have some vector minus A. What does it mean? Basically, that is there will be some vector. Let us suppose this is that vector we talked about. What will be minus A? Basically, this will be your minus A. Correct. This will be a minus A and this will be your plus A. So this will be your plus A, this will be your minus A. Okay, so what will be their sum? Their sum will be nothing but A plus minus A. Correct. Now since the magnitude of the two vectors are the same, it is quite clear the magnitude. So basically what is magnitude? Magnitude is nothing but the length. Correct. So magnitude is nothing but the length. The length of, as you can see clearly, that the length of both of these vectors are the same, but only a direction are opposite. Okay, so the resultant vector has zero magnitude. Quite evident, because length minus length will give you zero. Hence what we can say, that the addition, let us say I write this as equal to some vector z, and that magnitude of that vector z would be equal to zero. That is written here, that the resultant vector has zero magnitude and is represented by zero. So this is in bold, which is also called as a vector or a zero vector. So we introduce a new concept which is called a zero vector. Okay, so what is a zero vector? A zero vector is a vector. Let me write it here. A zero vector is a vector which has zero magnitude. So basically So A minus A is 0 bar. 0 bar or in bold 0, and the magnitude of this 0 is 0. Okay. So till now we have understood basically three types of different names of vectors. The first one is a position vector, which tells you the position.
Recording in progress.
Not be specified, so we don't know the actual direction in which it is forming, but it is a vector. I am not saying, we are not saying from this line that there is no direction associated with it. The direction is associated, but it is just that it cannot be specified. Specification of the vector direction and not having direction are two different quantities. If it is having no direction, then it would be called as a scalar. But if it is having direction, but the direction cannot be specified, then it is a vector only, as long as it is having some magnitude. Okay, so please look into the scenario very carefully. Okay, fine. So since the magnitude of a null vector is 0, its direction cannot be specified. Quite fine. Then the null vector also results when we multiply a vector A by the number 0. So what is happening here? As we understood in the previous example, when we are considering multiplication by a real number, what we understood is, let us say there is a number lambda and we multiply this by an A, then here the thing which we get is nothing but a 0 vector. So if this is 0, if this is a 0 vector, then we will again get a 0 vector. That is the explanation we talked about. Okay, again a property of your vectors. Okay, 0 vector to be much more clear. Okay, so the null vector also results when we multiply a vector A by the number 0. Okay, what are the main properties? Okay, so what are the main properties of 0 vector? So first 0 property is that when we add some vector A with 0, we'll get another same vector A again. Fine. The second is that when we multiply some number with a 0 vector, you will get a 0 vector again. And third thing is, when we multiply 0 is a number here, 0 is a scalar here, with a vector A, we will get a scalar 0. Okay, so these are all the things which are associated with a 0 vector. Fine. Then what is the physical meaning of a 0 vector? Okay, consider the position and displacement vector in a plane as shown in the top left figure. So let us try to understand the same situation which we understood for the explanation of your position vector and displacement vector. Okay, now suppose that an object which is set at P at time t moves to P dash and then comes back to P. Okay, so basically it was at this location, it went to this location and then it came back to this location again. Okay, so what if it came back to this location, then what is it? So it came back to this location again. So what is its displacement? Its displacement is nothing but equal to 0, right? Because the initial and the final position are same. If the initial and the final position are same, then displacement is happening there, and displacement is having some value. Displacement is a vector, but how to quantify it? What we will write? We will write that what is the displacement here? Since the initial and the final positions coincide, the displacement is a null vector. Okay, so here displacement is a null vector. So what we can say, we can directly write that displacement can be written as equal to 0 bar. Okay, so that is how we can understand the fun of the application of your displacement vector. Fine. Moving forward, now let us move on to subtraction of vectors. Okay, so how do we do the subtraction of vectors? The subtraction of vectors can be defined in terms of addition of vectors only. Okay, so just to explain, so let us say that we have some vector A and we need to do A minus B. So in vector subtraction, what we say is that A minus B is nothing but equal to A plus minus B. How to do this? Let us suppose I try to explain to you here. Let us suppose there is some vector A, and let us suppose this is some vector B. Fine. So now, if the concept is being asked me to calculate the value of A minus B, what I will say that A minus B is nothing but equal to A plus minus B. Correct. If it is equal to A plus minus B, then what can I say? That what we need to do graphically, I will take A and I will add minus B into it. What is minus B? Basically, minus B is nothing but a vector which is having the same magnitude of B, but the direction of it is reversed. So I will just put B here in this direction, and finally I will do the vector sum. How to do the vector sum? Just keeping the tail of B on the head of A and just joining the tail of A to the head of B, and therefore this is the resultant, which is nothing but equal to A plus minus B, which is also equal to A minus B. So that is how you do the vector subtraction. Fine. Okay, so now let us read whatever is written here. So we define the difference of two vectors A plus B as the sum of vector A and minus B. Therefore, A minus B is nothing but equal to A plus minus B. Okay, it is shown in the figure. The vector minus B is added to the vector A. The vector minus B is added to the vector A, so that we get R2, which is equal to A minus B. Okay, so you can explain, please refer to the figure B here. So what they are saying, let us say this is that vector A. Okay, now if because this was the vector B, doing the minus B of this, we will get this vector. So what they just did, they added vector B here, and therefore R2 which we got was this. So R2 is nothing but equal to A minus B. Okay. Similarly, just for your reference, they have added R1 is equal to A plus B also here. So you can understand that R1 is having same different magnitude also, different direction also than your R2 supposedly here. Okay. So that is how you can understand vector addition, subtraction also from the same concepts. Okay. So therefore the vector B is added to vector A to get R2, which is equal to A minus B. And the vector R1 is nothing but equal to A plus B is also shown in the figure for comparison. So this is your R1, which is vector addition, and this is your R2, which is basically your vector subtraction. Okay, fine, let's move on. We can also use the parallelogram method. To find the sum of two vectors. So now let us understand the parallelogram method. Previous to this, what we understood was triangle law of addition of vectors. This was the thing which we was introduced to us first. Now we will be understanding the parallelogram method. So let us understand this. Okay, so now suppose we have two vectors A and B. Okay, so let us say this is that vector A and B. Okay, so first of all, let me explain it here. Let us suppose this is that vector A and this is that vector B. Okay, so what basically the parallelogram law of addition says that you draw one imaginary line at this location at the head of A, okay, similar to the length of B. So this has a magnitude which is let me write it. 1 minute. So this is your vector A, this is your vector B. Okay, so what they are just saying that draw a imaginary parallelogram such that the length of this is nothing but equal to the magnitude of vector B, and similarly draw a line like this so that the magnitude of this is nothing but equal to the magnitude of A. And also the direction of this line is parallel to this line, and the direction of this line is parallel to this line. Right? So you do this thing. When you do this thing, finally, so as you can see, this vector A, this vector B, this was being drawn and this was being drawn. So finally, the resultant is nothing but the resultant has the magnitude which is equal to the diagonal from the origin O to the outmost point, that is S, and the direction is basically of the diagonal. So the diagonal of this parallelogram is basically the resultant of the two vectors addition, that is A and B. Fine. So that was being explained here. So now let me just iterate and explain you again. So we can use a parallelogram method. Suppose there are two vectors A and B. So to add these vectors, what we did, we bring their tails to a common origin O. So what we did, we bring their tails. As you can see, the B is also having this as the tail, and A is also having this as the tail. Okay, so we bring their tails to a common origin O as shown in the figure A. Okay, so this was the figure A as a reference. Now then we draw a line from the head of A. Now what we did, and we draw a line from the head of A to B, and another line from the head of B parallel to A. So basically we draw a line which is parallel to B and similarly draw a line which is parallel to A, like this. Okay. To complete a parallelogram OSQP, so it's OQSP, sorry, OQS, fine. So next thing states that now we join the point of intersection of these two lines to the origin O. So now what we are doing is, we are joining this point of intersection. This is that point of intersection of these two lines. As we can see, this is the one we are just joining it. Okay. So when we try to join this line here, it is saying that the resultant vector R is directed from the origin O along the diagonal OS. So this is O, this is S, and this is the resultant being explained to you. Okay. So that is the parallelogram, which is written in figure B here. Next line states that in figure C, this is the figure C, the triangle law is used to obtain the resultant of A and B, and we see that the two methods yield the same result. Okay, so as you can see, that the two methods are yielding the same result. Thus, the two methods are equal. I will try to explain again how the parallelogram of vector addition and the triangle law is same. Okay, let us suppose this is vector A, and let us suppose this is some vector B. Fine. Okay. So first of all, let us try to understand this using the parallelogram law. Parallelogram method. So using parallelogram method, what we can say, what is the complete procedure? First of all, we will bring the tips of both at the same location. So let us bring the tip at the same location, and this will be A, this will be B. Now I will draw a line which is parallel to this, and similarly I will draw a line which is parallel to A. It will join at a location. Let me call this point as C, and let us say this is the point O, and what will be the resultant? Resultant will be this quantity. Let me write this line as R. Okay. Similarly, let us conceptualize this using triangle law of addition. So using the triangle law of addition, what we can say? So how can say it? So basically, what I did, this was my B. Okay, so as we know that it follows a commutative property, so either I can explain it like this, or I can explain it in opposite sense also. So first of all, let me explain it like this. So I can keep my A at this location. Okay, so what is basically vector addition? Just I'm adding it like this, correct? So this is your vector R. So this vector R is nothing but also equal to A plus B. I can do it in another sense also. Let us say this is the vector A, and this is your vector B kept here. Right, so what is the resultant? The resultant is nothing but this. Fine, so this is again vector R, which is equal to A plus B. So as you can see clearly from each of these senses here, the vector R is having the same magnitude and it is also having the same direction. So that is how we can understand the parallelogram method and the triangle law of addition. Okay, fine. So let me close this and let's move forward. Okay, so now let us try to understand this example. Okay, so the rain is, I think this example would be understood. Okay, so let's leave this example for now. This example is for future works. That we will understand this afterwards. Okay, so ignore that thing. Let us now start a new topic, that is resolution of vectors. Okay, so in resolution of vectors, we will try to understand, as the name suggests, resolution. So what you will understand, okay, so after explanation, I will try to explain to you what does resolution actually means. Okay, so first of all, let's start this topic and then we can understand the basic meaning of this resolution. Okay, fine. So resolution of vectors, let's understand this carefully, and so that we can understand the analytical expression behind all these topics. Okay, fine. So let A and B be any two non-zero vectors. Please remember, we are not conceptualizing about zero vectors here. These are some non-zero vectors. Okay, so it is explained here also in the figure. Let us say these are the two vectors being explained. That is, let A and B be any two non-zero vectors in a plane with different directions. So the direction of this is also same, so that they may not be equal and they will not have the same magnitude also. Okay, and let capital A vector be the another vector in the same plane. Let us say this is that vector A being talked about here. Okay, now A bar can be expressed as a sum of two vectors. A bar can be expressed as a sum of two vectors What are those two vectors? One obtained by multiplying a bar by a real number, and the other multiplied by multiplying b by another real number. Okay, so what it is saying, try to understand. This is one of the great quality of a vector. Okay, so what they're saying, let me have some two random vectors. This is small a vector, and let us say this is small b vector. As long as those are not in the same direction. Okay, now what they're saying is that if I have some vector a, this vector a can be said as equal to summation of two vectors a and b with some multiplication factors added to it. Okay, so basically this vector a can be found out if I just multiply this vector a bar, small a bar, by some factor lambda, and this vector b bar by some vector mu. Okay, so basically we are just trying to increase the length and length such that when we add mu b into it, we will get this direction of a. Okay, let us try to understand this again. Okay, so let us say we are trying to devise a concept here. Okay, let us say this is the a bar which we know, fine, and let us say that this is the value of a we knew, and and this is the value of let us say b we know. Okay, now what we are saying is that let us say we have multiplied lambda into this. Okay, so what will be the, let us say this was increased and this was your lambda a now. Similarly, now so I can conceptualize lambda a like this, right? Now let us say the factor which I added to mu, which was mu, was very small. So the length would have been something like this only, right? Then what would have been the value of resultant vector? This would have been like this. Let us try to increase it. Let's say this is till here. And what would have happened? The resultant would have gone here. Okay. Let us increase it more. It would have gone here. Right. So as you can see, there would have been some vector a, there would have been some value of this mu and some value of this lambda, such that when we add lambda a plus mu times b, we would have got the direction also correct and the magnitude of this length also correct. Okay, so that is how we can use two different vectors multiplied by some factor, and then we can calculate or find some another vector third. Please remember, all this is happening here in one plane only. Let's not increase the complexity. Let's understand it step by step only. Right now, what we can say, that some vector a bar can be said as multiplication of two different vectors, lambda times a and mu times b. So I explained you how this thing can be obtained. Okay, let's move on then. So to see this, what we did, let o and p be the tail and head of vector a. Okay, so what they are saying, let o and p be the head, let o and p be the head and tail. So this is your basically head and this is your basically tail of vector a. Then through o, draw a straight line parallel to a. Through o, draw a straight line parallel to your small a. So we drew a straight line like this, right? And through p, draw a straight line parallel to b. We drew a straight line parallel to b. Okay, let them intersect at q. Then we have what is a, which is equal to op, is nothing but equal to oq plus qp. Okay, so this may be a little confusing here. I will try to explain this again. So what they just said was, let us say this is some vector a. Now what we know that, okay, so there was some vector small a which had this direction, and let me draw it here only. Let us say this is some vector a. Okay, so now we knew that there was some vector small a which was having this direction like this, and there was some vector b which was having some direction like this. Okay, what we just did, this was your point o, this was your point p. What we did was we made a line which is parallel to your small a vector direction. Similarly, what we did was we drew a line which was parallel to the vector b direction. Okay, so they are saying that these two vectors, so these two lines intersected at a point which we now denote as q. So what we can finally say, that if we multiply a by some lambda value, that value may be different. So that value can give you this new vector. Similarly, if we drew a if we multiply some new value, then we can get this vector also. Correct? So that is how this lambda and mu value can be obtained graphically. Okay, so we can just measure it. We know the magnitude of small b, we know the magnitude of mu b. So mu can be obtained directly as mu b by mu b by b will give you the magnitude of mu. Similarly, can be happened for lambda a also. Okay. So therefore, what we got is that a, which is equal to OP, is nothing but OQ plus QP. So this is nothing but triangular method of vector addition written. Fine. So it's, as you can see, it's OQ, QP. So basically, we added like this. Okay. But since OQ is parallel to A, and QP is parallel to B, we can write OQ as sometimes lambda times A and QP as mu times B, where mu, lambda and mu are real numbers, and therefore finally what we got is A vector is nothing but equal to lambda times A plus mu times B. So that was the final conclusion of this lecture slide. Okay, now we say that A has been resolved into two components. Okay, so that is how this word came into picture, resolve or resolution. So what we say that A has been broken down into two different vectors. Namely, what are those vectors? Those vectors are lambda A and mu times B. Or else we can say that vector A is being resolved. Okay, so that is how this word resolved came into picture. So we resolve the vectors, right? Okay, let's understand further. So we say that A has been resolved into two component vectors. What are those vectors? First is your lambda times A, and second thing is a mu times B along A and B respectively. Okay, fine. Let's move on. So using this method, one can resolve a given vector. What does it mean by resolving a given vector? Basically dividing it into two different vectors, addition of two different vectors. Okay. So one can resolve a given vector into two component vectors along a set of two vectors. All the three lie in the same plane. Quite evident, as you can see. A also, uh, lambda, capital A also, lambda A also, and mu B also. All are lying in the same plane only. Okay. In our case scenario, we can take it as xy. In our case scenario, we can take it as xy axis. Okay. Next thing is, it is convenient to resolve a general vector along the axis of a rectangular coordinate system using vectors of unit magnitude. Okay. So first of all, okay, it is convenient to resolve, again resolving a general vector along the axis of a rectangular coordinate system. So what they're just trying to explain you. So what we basically did was, there was some vector A which we resolved into two components which were having some arbitrary directions, right? So to make it much more clear sense, or to make it much more general, what we generally say is, let us say that these two vectors are nothing but in these directions. Okay, so these are basically those two vectors, and we say that the magnitude of this vector is basically 1 and the magnitude of this vector is basically 1 again. Hence, because the magnitude is 1, these are called as the unit vectors. Unit, as the name suggests, is a vector which is having unit magnitude. Okay, and we take this into scenario so that we can understand each and every concept using the rectangular coordinate system criteria. So here these two vectors will be perpendicular to each. Okay, so that is the explanation of how we came into the new concept, which we will understand after we understand the few points regarding unit vectors here. Okay, so just to understand this line again, it is convenient to resolve a general vector along the axis of a rectangular coordinate system, okay, using vectors of unit magnitude. These are called unit vectors that we discussed. So let us discuss first unit vectors and then we can move forward. Okay, so unit vectors. Okay, so this may be a new quantity now. So till now, what we are all the concepts which we have understood. The first was your position vector. The second was your displacement vector. The third was your zero vector. And now we are understanding the fourth point, that is unit vector. Okay, so now let us understand what is this unit vector. Okay, So a unit vector is a vector of unit magnitude. Quite evident. Let us say any vector which is, let us say this is said to be a unit vector, then the magnitude of this vector will be 1. Okay, so a unit vector is a vector of unit magnitude and points in a particular direction. Okay, so what does it say? It points in a particular direction. So that direction in our sense, or so this direction basically in our sense can be said, let's say that this is one direction and this is another direction. Okay, it has no dimension in unit, quite evident. It has no dimension in unit. It is used to specify direction only. So it is used to specify direction only. Unit vectors. Now this is a very, very important line because this is the basic crux of how you're understanding the vectors. Everything which you will do from now on will be in terms of this fourth point which has been explained here. Okay. So unit vectors along the x, y, and z axis of a rectangular coordinate system. Okay, rectangular coordinate system. The unit vectors which are along what? Which are along the x, y, and z axis of a rectangular coordinate system are denoted by. So this is being read as I cap, j cap, and k cap. So it's I cap. So this is called as I cap. Similarly, j cap and k cap. Okay, so there's a cap being obtained over ijk, and hence these are nothing but a representation way of unit vectors. Okay, so they are denoted by I cap, j cap, and k cap respectively, as shown in the figure A. As you can see, this I cap is along the x-axis, this j cap is along the y-axis, and this k cap is along the z-axis. All these will have a magnitude equal to 1. So since these are unit vectors, since these are unit vectors, we have mod of I is equal to mod of j is equal to mod of k, which is equal to 1. Okay, fine. So that thing is also explained. Fine. So that thing is also explained. Now let next thing is, now these unit vectors are perpendicular to each other. Okay, so quite evident, as you can see also from this diagram, that all these are perpendicular to each other. I is perpendicular to j, j is perpendicular to k, I is perpendicular to k, etc. Okay, so these are the only three ways. Fine. So these unit vectors are perpendicular to each other. In this text, they are printed in bold face with a cap. So this is basically cap to distinguish them from other vectors. Okay. Since we are dealing with motion in 2 dimensions in this chapter, we require only 2 unit vectors. So majority of this concept will be understood using Ij only. So there is very little or no requirement of generally in motion or state motion in a plane. In this chapter, majorly we will require only I cap and j cap. Okay. So now if we multiply, so now these are just the properties of unit vectors. So now if we multiply unit vector, say n cap, by a scalar. Okay, so now we are saying that n cap is a unit vector. By a scalar, the resultant vector will be lambda. Lambda would be the vector. Okay, so because lambda would become the vector as lambda times n cap. Okay, so just to explain it, what is actually happening here? Let us say this is that vector n. Correct? What is the magnitude of this vector? The magnitude of this vector is 1. Correct? Now we have some vector which is a. Okay, so what will be the magnitude of this vector? The magnitude of this vector is, let's say, a only. Let us suppose. Okay, so now what will I multiply? Let us say that these both have same direction. Let us say these both have same direction. Then what will happen? What if I have to write a vector such that I have to multiply this. Let us say I need to multiply this by a quantity such that it is the magnitude of this unit vector is equal to the magnitude of a. It is quite evident that this lambda into 1 should be equal to magnitude of a, and therefore lambda should be equal to e. Hence we multiply, so that therefore what we get is a times n vector is nothing but equal to a vector. So that is how this thing can be explained. Fine. That thing being said, so in general, a vector a can be written as equal to nothing but a vector, which is equal to mod of a into n cap, n here. Okay, so I explained to you this quantity. Now similarly in general, we can write it like this. Okay, so what is vector a? Vector a is nothing but equal to magnitude of vector a into unit vector n. Okay, so it is vector A, or else let's not write here. Let me write it here. So A is equal to mod A N. Okay, so this is nothing but vector A. This is nothing but magnitude of vector A, and this is nothing but unit vector. Fine. So that was the explanation being done for this part. So where n is a unit vector along. So this is a very important line that we are assuming that this time n is a unit vector which is along A1. Okay, fine. That being said, we can now resolve a vector A in terms of component vectors that lie along unit vectors I and j. So what does it try to say? So in the previous example, what we did was, in the previous example, when we started as you understanding the resolution of vectors, what we understood was there was some vector A. It can be written as equal to some lambda times A vector plus some mu times your B vector, right? So similarly, what we can say that again this vector A can be written as equal to some lambda times I vector plus some mu times J vector. Correct? Yeah, these are some unit vectors only. Okay. So what will be actually happening? This will be your lambda I. This will be your mu j, and therefore depending upon the magnitude of these values, these vectors, we can get the value of a. We can get the value of a, right? So that is how vector A can be explained. Okay. For more general purposes, this can be written as equal to ax because it is in x direction plus ay because it is in y direction. So vector A is nothing but equal to ax I cap plus ay j cap. Fine. So let's understand again. So we can now resolve vector A in terms of component vectors that lie along unit vectors I cap and j cap. Now consider a vector A that lies in the xy plane as shown in the figure B. We draw lines from the head of A. We draw lines from the head of A perpendicular to the coordinate axis as shown in the figure B and get vectors A1 and A2 such that A1 plus A2 is equal to A. Since A1 is parallel to I cap and A2 is parallel to J cap, we have A1 is equal to AX I cap and A2 is equal to AY J cap, where AX and AY are real numbers. Whatever is written here, I will try to explain to you in this diagram here. So what they are just saying, let us suppose this is the coordinate system we have. This is the coordinate system we have. Okay, so this will be your x-axis. This will be your y-axis. We have just understood this point that this is basically the direction of your I cap, and this is basically your I cap now, and this is basically your J cap. Okay, now what they're saying next thing is that let us assume that there be a vector A. Let us say this is that vector A. Fine. Now what was the next line? You just draw perpendiculars from it. So let us say this is the first perpendicular being drawn, and let us say this is the second perpendicular being drawn. Okay, so it reaches this location. It reaches this location. Okay, so what we assume from this point again? So basically, they are saying that this is nothing but your A1, and this not this. So this is basically your A2. This is basically your A2. Drawing it again here, so what it says that this is your A1, this is your A2. Therefore, from the parallelogram law of addition, what you will get? This is your vector A, right? So what is vector A basically? Vector A is nothing but equal to A1 vector plus A2 vector, correct? Now, again, just we are changing the terminology here. So what we are saying that what is A1? A1 will be nothing but A1 vector is nothing but equal to some AX times I cap. So some AX value is just the magnitude value. And similarly, what is A2 vector? A2 vector is some AY times. AY is another number here times J. So finally, what we got is that A vector is nothing but equal to AX I cap plus AY J cap. So that is the complete explanation which was being explained to you in the last two lines. So that is the complete explanation which has been explained in these lines. Fine. So A1 is equal to AX I cap plus A2 is equal to AY J cap, where AX and AY are real numbers. Thus, Finally, what we got is, what is the final conclusion? That A is equal to AX I cap plus AY J. Okay, what is the name of the topic here? It is resolution of vectors. So what we basically did, we had a vector, we resolved this vector. Please remember, we resolved this vector into two different components, which were AX I cap and AY J cap. So that is how the name resolution came into picture. Okay, let's move on. So this is represented in figure C. So as you can see, this is how it is represented in figure C. So what is A? A is nothing but equal to AX I cap plus AY J. Okay. So the quantities AX and AY are called the X and Y components of the vector A. Now this is to just the theoretical part, that the AX value is called as the X component and the AY value is called as the Y component. Okay. In the future prospect, we will understand that how to calculate it, and then in the next prospect we will understand the addition of this vector by analytical concept. Okay, fine. So note that AX is itself not a vector. Okay, so this is very important point. Please note that AX is itself not a vector, but AX I cap is a vector, right? So as similarly, A is not a vector, but mod A, vector A, when it is multiplied by some value into n cap. So this is basically a vector, correct? So that is only written here. So basically, AX is not a vector, it is scalar only, but AX I cap is a vector, and similarly AY J cap is a vector. Okay, so because we are just multiplying I cap with some factor, and similarly J cap with a factor, so therefore that complete value becomes a vector. Okay. Using simple trigonometry, we can express AX and AY in terms of the magnitude of A and the angle theta with which it makes with the x-axis. So how it is being explained, let me explain to you. So let us suppose this is your vector A. So this is the small simple concepts only. There is very easy trigonometry being involved here. So this is your theta, correct? Let us say this is the magnitude AX I cap and this is AY J cap. So if we need to just calculate about magnitude, so we know that what is cos theta and what is sin theta, right? So basically cos theta will be nothing but equal to your AX upon A, and similarly sin theta, so it is the magnitude part always, and similarly sin theta will be equal to nothing but AY upon A, right? So if you make a triangle like this, if it is supposedly take this triangle ABC, can calculate each and everything here. So therefore what we got is that what is magnitude of AX? Magnitude of AX is nothing but equal to, or just AX. Let's not go into, because AX is itself scalar only. So what is AX? AX is nothing but equal to A cos theta, right? And similarly, what is AY? AY is nothing but equal to A sin theta. Correct? So this is the mathematical form. That is also written here. So AX is nothing but equal to A cos theta, and similarly AY is nothing but equal to A sin theta. Okay. As is clear from the above equation, a component of a vector can be positive, negative, or zero depending on the value of theta. Okay, so we all know that what is the range of sin theta? Sin theta can be in the range of sin theta can be in the range of -1 to 1 with -1 and 1 included. Similarly, cos theta can also be in the range of -1 to 1. Correct? So depending on, let us say, if A are positive values, then if sin theta is negative, then the value AY can also be negative. Hence, these vectors or these components of the main vector A can be positive also, negative also, or even zero also. Because let us say if theta is 0, then AY will be 0. Or let's say theta is 90, then AX will be 0. Okay. So depending upon that, the vectors can be positive, negative, or 0. Fine. Next thing is, now we have to specify two ways to specify a vector in a plane. Okay, so this can be specified by, the first is by using its magnitude and the direction it makes with the x-axis, and the second is AX and AY. Okay, so what is the first way? The first way is just that, let us say this is that vector A. I just say that this is that vector A, and it is at an angle with the x-axis. Or another thing is that I gave you the values of AX and AY. So you know the value of AX, you know the value of AY, we can calculate the value of A. How can we calculate, or how can we say it on graphical terms? It is nothing but the resultant of the parallelogram radius. Fine. So that is how you can specify two different ways to specify a vector. So first is the magnitude A and the direction theta. So magnitude of A is required in the first one, right? So when we draw it like this, we should know the magnitude of this, and second thing is we should know the angle. Then that is how you can make an arrow like this, okay, with an angle theta. And similarly, if you know the AX and AY, it was simple only. You just need the parallelogram law of vector addition, and you can find out the vector A. Okay. So that is being explained. So these were the two method specifications. First was its magnitude A and the direction theta it makes with the x-axis, and second its components AX and AY. Fine. Let's move on. So if A and theta are given, AX and AY can be obtained using above equation, which uses simple trigonometry. Okay. So now let us move into the more understanding about it. Okay. So what they're saying is that we know only A and theta. Let us say we just know A and theta. We need to calculate the value of AX and AY. Okay. So how it can be obtained? So if AX and AY are, this can be obtained directly, as AX is nothing but equal to A cos theta and AY is nothing but equal to A sin theta. Now let us reverse the situation. Now. Let us say that AX and AY are given. Okay. So if AX and AY are given, we need to calculate the value of A and theta. So how to do that? Okay. So simple mathematical calculation, nothing involved. So just see here whatever I'm doing. So as we know that AX is nothing but equal to A cos theta, first thing, and second thing we know is AY is nothing but equal to A sin theta. Correct? So now let us calculate AX square plus AY square. So this will be equal to nothing but A square cos square theta plus A square sin square theta. If you take A square common from it, we will get this is equal to sin square theta plus cos square theta. What is sin square theta plus cos square theta? It is always 1. It is A square into 1, which is equal to A square. So this is the first relation which we got, which is the summation of the two components squared is equal to the magnitude of vector squared. Okay. So therefore, what we can say that if we know the value of AX and AY, we can obtain the magnitude of A as nothing but equal to AX square plus AY square. Please remember it to much more clarity that this is only and only valid if AX and AY are the two factors which are being multiplied with unit vectors only, or they are at 90 degrees. If the angle changes, if the angle between I and J, or let's say any two vectors changes, then the formula also changes. Okay, so this is only and only valid because I and J are 90 degrees or perpendicular to each other. Fine. Moving on, so from tan theta, so tan theta is nothing but can be directly obtained using the diagram shown in the figure C. So tan theta is nothing but equal to, this will be your AY, this is AX given to you, so this will be equal to AY by AX, or we can write this as equal to theta, which is equal to tan inverse. So tan inverse is basically just inversing the keeping on the right hand side. So tan inverse AY by AX. Fine. Okay. So this thing is explained, this thing is explained. So basically, if you know AX and AY, we can obtain A also, theta also. And if you know A and theta, so it can directly obtain AX is nothing but A cos theta and AY is nothing but equal to A sin theta. This is being explained. Okay, fine. Next thing is, so far we have considered a vector lying in an xy plane. The same procedure can be obtained to resolve a general vector A into three components along x, y, and z axis. Okay, so then what would have changed? Only AX was A cos theta, AY was A sin theta, but then this would have been AZ is equal to some another parameter would have come. Okay, so it is just for your reference, because it is not as much required right now, just for reference, because we should know how can we upgrade this quantity, correct? So if alpha, beta, and gamma are the angles between A bar and x, y, and z axis, so because the angles, if you look at it very carefully, the angles for x axis, for y axis and z axis would differ. So try to understand the situation very carefully. Therefore, the components along x, y, and z axis would also differ. All the angles would be different this time. Okay. Therefore, AX will be equal to A cos alpha, AY is equal to A cos beta, and AZ is equal to A cos gamma. Okay, so in mathematics, when you will understand the 3D geometry, then this concept of A cos alpha, beta, and gamma will be much more clear, because you will be you will revolve around these all concepts only in this chapter. Okay, so let's be hesitant right now. We will understand this much more clearly when we will go through that mathematics chapter. Okay, fine. So finally what we obtained is that we can resolve this in 3 components here also. Fine. So let's stop the discussion here. We will move from the further discussion in the next part of this lecture. Okay, so let me stop it here. So right now we have done with the introduction part. The course for the course progress, scalars and vectors is done. Multiplication of vectors by real numbers is done. Addition and subtraction of vectors, graphical method is done. And right now we are on the resolution of vectors. The resolution of vector will be completed by the starting of the next lecture, and then we can start with the vector addition, that is analytical method. Fine. After that is over, we'll move on to the basic concepts regarding motion in a plane, and then we can move on to projectile motion, uniform circular motion, etc. They are very, very, very good topics, very informative topics. So we will give proper time to all of them. Fine. So that's it for this lecture. Thank you so much.